In the previous video, we have seen about how mutual electric fields interact with each other and how it creates force between two charges. Now, in this video, we're going to learn about superposition of charge. Now, what is superposition of charge? So let's say here we have a charge, what we called as Q1. Now, this charge can experience force by the charges surround itself. So let's say here we have another charge, which what we called as Q2, and there's another charge what we called as, let's say, Q3, right? And there are so many charges surrounding each other. Let's say here we have another one, and this is another one, and this is another one. So one second. So there are so many charges here that applies force on this Q1 charge. So let's write it down there. So this is Q2, Q3, and this is, let's say, Q4, Q5, and Q6, right? So now in this situation, Q1 charge, this is the white one, so the Q1 charge experiences force from every side where another charges are placed. So let's say the Q1 charge and Q2 charge, so the Q1 Q2 actually creates a kind of Coulombian force between these two. So the distance between them, let's consider it like R1 vector, right? So whenever we write R1 vector or maybe R vector, we actually write R into R cap. So R will tell you the magnitude form, so it's the magnitude form, right? So it tells how much distance actually is, and the R cap is basically tells the direction of the distance, means direction of the charge, like this charge is Q1, and from here the Q2 charge, where the Q2 charge is placed, in which direction the Q2 charge is placed. So basically it's R1 vector from this side. So now the force between these two charges is basically what we call as F12, obviously, because we have the Q1 charge and we have the Q2 charge. So the force between these two charges is F12. Now the force between these two charges can be written as by the Coulomb's law. So F12 would be equal to basically K Q1 Q2 over R square. Now in this situation, we can we only write the scalar form of the Coulombian force. We can also write it its vector form as well. So F12 vector is equal to K Q1 Q2 over R vector square, which is actually the magnitude, multiplied by R cap. So what R cap tells, it tells the direction of force, right? So this is basically a force between these two charges. Now there's not only one charge, there's so many charges that applies force on this Q1 charge. So that depends on the distance between the Q1 charge and another charge. So now let's deal with this Q3. So the Q3 is separated by the Q1 charge with the distance, let's say this distance is R2, right? So this is R2, or maybe we can write it in a 2 form, like when we write distance between Q1 and Q2 charge, we actually write R12, and when we write the distance between Q1 and Q3 charge, we actually write R13, right? So this is more specific and more clear. And as well, the distance between the Q1 charge and Q6 charge, maybe the first one is Q4, so Q4 charge would be R14 vector, and this distance would be R15 vector, and this distance would be obviously R16 vector. So all charges will apply force on this Q1 charge. So what superposition of charge will tell that all forces, or maybe the net forces on a specific Q1 charge is equal to the vector sum of all individual charges, right? So basically first charge is imposed on a Q1 charge is F12. Now the second charge impose force on where is what we call as F13. So Q3 charge actually impose force on a Q1. So basically F13 would be equal to obviously K Q1 Q3 over R, and when we write the distance between them, so we actually write R13 mod a square and the distance R cap, actually the vector R cap, right? So all kinds of force will act on a Q1 charge. So the total charge, according to the principle of superposition, actually the principle of superposition, superposition. So what actually it says that the total force, so the total force F net is actually equal to the vector sum of all forces. So our first force is equal to the F12. So okay, let's write it with the white marks, the white color. So F12 vector plus F13 vector plus F14 vector plus F15 vector and plus F16 vector, right? So since we have 5 charges surrounding the Q1 charge, so we actually added all the forces in its vector form to get the net force on a Q1 charge, right? But let's say if we consider n charges surrounding this Q1 charge, so if we have n charges, so for n charges we can write it that for n charges, right? Once again, n charges surrounding once again n charges, oh it's my bad, so if n charges surrounding q1 charge. So let's say q1 charge is surrounded by the n charge, so the net force would be obviously the vector sum of all forces acting on that particular charge. So this is f12 vector plus f13 vector and dot 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 dot, it would be f1n vector, and that will tell you about the net force on the first charge, which is q1, right? So this is the principle of superposition that will tell you the vector sum of the total force acting on a charge. So now from here we can write it as electric field as well. So let's say first of all we can write this net force in the form of its summation. So we use actually a sigma, which is a mathematical tool for the addition of these all forces, the vector forces. So the net force will be, we can write that the net force would be equal to the sigma of F1, and the another charge would start with a 2. So let's say here we have a since we have q1 charge in the center, and another charge would start with the q2, q3, q4, q5, 6, q6 and so on. So that would be f1i, right? So f1i vector, and from here I is equal to 2, and from 2 to let's say n. So this is the summation form of the net force acting on q1 charge. So from here we can write it as the expression for the force. So basically it's equal to the sigma. Now the expression for the force between any two charges would be equal to 1 over 4 pi epsilon naught, which is actually the Coulomb's constant here, right? So 1 over 4 pi epsilon naught, and q1, our first charge is q1, which is experiencing the force, and another charge is qi. So basically qi depends on the q2, q3, q4 or whatever, and the distance between them is actually r1 and I. So distance always depends on the where charge is placed. Like some charges are separated with a very less distance, like they're closer to the q1 charge, and some charges are farther from the q1 charge. So it depends on the distance between them, so it is basically 1i, and we have to write square because the force is equal to 1 over 4 pi epsilon naught q1 q2 by r square. So now we also have to write I is equal to 2 to n. So the net force would be equal to, now we know that the sigma is a summation, and the summation is possible only for the variables. Constant would be, separated out. So 1 by 4 pi epsilon naught is outside of the sigma, and now what remains is q1, right? q2 which is qi, and r1i square, which is I is equal to 1 and n. Now q1 is also a kind of a constant, but it is multiplied by the qi. So we actually write the net force, the expression for the net force, in this form, right? So you probably get this, that the second charge, our q2 charge, is variable and the first charge is constant. So the charge experiencing the force, which is here the Coulomb's the q1 charge, is constant, and the q2, q3, q4, q5, q6 is just a variable charge, and the distance between them is also variable, right? So now this is also possible for the electric field as well, because the principle of a superposition is not only for the force, it is actually for the electric field as well. So for the electric field we can write that for the electric field, for the electric field. Now we know that electric field also have a direction. So let's say here we have here we have a q1 charge here, and there's another charges that we have written q2, and there's another charge which is what we call as q3 and q4 and q5, and let's say there's a q5 and q6, right? So these are all charges surrounded to the q1 charge, and let's write here. So this is q2, this is q3, this is q4, right? This is q5 and q6. Now all charges have its own electric field, and it is directly imposing the electric field on q1 charge, right? And it depends on the nature of charge. Like if there's a positive charge, like let's say q2 is a positive charge, so positive charge actually have an emerging electric field from the q2 charge. So basically this is electric field emerging from the q2 charge. And let's say q3 is a negative charge, so this is electric field going towards the q3 charge. So we have seen that the positive charge has an emerging electric field, and the negative charge has an electric field going towards the charge, or maybe the inside the charge. So all kinds of electric field applies on the q1 charge. So this one, and this one, right? So maybe all are positive, so it all has the emerging electric field. So q4, q5 and q6, well, it depends on the charges, the nature of charge. So what the principle of superposition for the electric field tells you about the electric field, the net electric field. So this is this is q1 charge, so the net electric field, E net. So the E net would be equal to the vector sum of all electric fields individually. So E1 plus E2 vector plus dot 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 if there are n charges. So first of all we have to write it for the 5. So E2, sorry, I have to start with the E2, right? Because E1 is the electric field due to the first charge. So E2 vector plus E3 vector plus E4 vector and E5 vector, right? So and E6 vector. Now in this scenario we only written only one term. So let's say E2 electric field. So this E2 electric field is the electric field due to the second charge. It is not like E12. So E12 is it's never possible, it's not possible. So F12 is possible because it is the mutual force between two charges. So this is, let's say, q1 charge and this is q2 charge. So F12 is possible, but E12 is not possible, it is individual. In the previous video we have seen that this is the mutual electric field that interacts with each other and creates a force. So if we have a kind of charge q1 and if there is a charge q2, so q1 charge has its own special electric field E1, and the q2 charge has its own particular electric field E2. So these are the different electric fields that actually interact with each other and creates a kind of force, which what we called as Coulombian force. So that's why we have written here that the net electric field on the q1 charge is basically the vector sum of all individual electric fields applying on the q1 charge. So this is this is applicable for the n charge as well. So for the n charges we can write this as the net electric field on the first charge is equal to the E1 vector plus E2 vector and plus dot 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 En vector, right? Oh, I'm sorry. So this is the total electric field, the formula for the total electric field when it is surrounded by many charges, right? And we can also write it in the form of summation. So sigma. So the net electric field would be equal to the sigma E and I. Okay, so do I have made mistakes here? We should have start with the E2, and from E2 there should be E3 and E4 and E5 and then En. So if we do summation of electric field, so we have to write it sigma Ei, and I starts with 2 and goes up to n. right? So this is the form of electric field, the summation of electric field. Now this can also be written in the form of its formula. So basically the electric field formula is 1 over 4 pi epsilon naught q I over r square. Now r depends on the distance between them, so r 1I. So the distance could be written as 1I and square, right? So we can separate out the constant term. So constant term would be 1 over 4 pi epsilon naught, once again 1 over 4 pi epsilon naught sigma qi over r1I square. Now in the vector form, since we are written in the vector form, we have to write it like this. We have to multiply it by the r cap and r cap. So do you get this, that how principle of superposition works? All right, so let's dive deep into it. Now there's more point that these charges, like here we have a q1 charge here, and this q1 charge is surrounded by many charges, q2, q3, q4, q5 and q6. Now these charges, the surrounded charges, do not intersect or do not interact with each other. So this is given that the q2 charge will never interact the q3 charge, as well as q3 charge would never interact with the q6 charge. It all acts individually on the q1 charge. So this is a main point that you should remember in the principle of superposition for the force and for the electric field as well, that the only individual charges works on the q1 charge. So let's say if q2 charge interacts with the q3 charge, so actually it will hinder the both charges, and maybe it can reduce the kind of force or maybe the electric field to some extent. So let's say here we have a kind of three situations, like a situation of a three charge. So let's say here we have a q1 charge and there's another charge q2 and q3, right? Maybe this one, once again. So this is q3, a second, this is q3, right? So in this scenario we are dealing with the forces on q1 charge. So basically the distance between them is r12, right? This is q1, and the distance between them, the q3 charge, is r13. Now if let's say q1 interacts with q3, then it actually hindered the interaction between q1 charge to q2 and q1 charge to q3. So this is given that all other charges, the surrounded charge do not intersect or interact, do not interacts with each other, do not interacts with each other. Surrounded maybe charges do not interacts, once again, interacts with each other, right? So this is the important point that you should know, that any other charges surrounded by the q1 charge, surrounded the q1 charge, would not interact with each other, because if they interact each other, then it will hinder the effect on q1 charge, like it is applying the force on it. So the f12 will hinder, and q3 charge is also applying force on a q1 charge, so f13 will hinder to some extent, to some degree, as well as the electric field would also hinder. So we are only dealing with the individual forces and the individual electric fields. So this principle of superposition works only for the individual summation, right? So this is what we have as the principle of superposition for the electric field and the principle of superposition for the force, right? So this is very important that you should know that the charges should only added, the force should only added individually, and what we have written here is f12, f13 and f1n. So these are all just individual forces. This f13 is also individual, as well as electric field e2, e3 and en. These are all just individual electric fields, right? Now let's take an example. So here we have a question that let's say in the center here we have a charge of maybe 2 coulomb, right? Now this 2 coulomb charge is surrounded by a second charge of, let's say, 4 coulomb, and another charge, once again, and then another charge is, this is let's say 6 coulomb. Now we have to calculate the net force on this q1 charge. So the net force would be, now how can we calculate? So q1 charge is given 2 coulomb, q2 charge is actually 4 coulomb, and q3 charge is 6 coulomb. We have to calculate force, or maybe the net force on q1 charge, right? So for calculating the net force on q1 charge, we have to apply the principle of superposition in this scenario. So let's say the distance also is given. So the distance between these two charges, the 2 coulomb and 4 coulomb, is let's say 2 meter, right? For the simplicity, we use meter as a SI unit and coulomb as a the SI unit for the charge, and the distance between these two is, let's say, 3 meter, right? So now if we have to calculate the net force on the q1 charge, we have to write it, the force between first and second charge plus the force between first and third charge. Now we have to calculate individual forces, and then we have to add for the net force. So first force would be F12. Now how can we calculate? It is equal to the 154 pi epsilon naught q1 q2. Now the q1 is q1 q2 over r square, which is basically r12 square, right? So the 1 by 4 pi epsilon naught, let's not write the value of the 1 by 4 pi epsilon naught, we will write it in its common form. So 1 by 4 pi epsilon naught here, and q1 q2 is basically 2 coulomb and multiplied by 4 coulomb, and the r12 is basically the distance between first charge and second charge. So this is 2 meter, so the 2 meter a square, right? So if we solve this one, so 1 by 4 pi epsilon naught, right, and 2 into 4 would be which is equal to the 8 coulomb square and over 4 meter square. So 4 is divided by the 2, so which is actually, now we can write force 12 as force 12 as 1 by 4 pi epsilon naught k, right? So this, which is basically 2k Newton. K is the Coulomb's constant, obviously we know, and the simplification of these q1 q2 over r square is 2. Now the first force is 2k Newton, this is 2k Newton. Newton is the SI unit of the force. Now if we calculate the second force, which means this the second charge due to the third charge actually, so F13 is equal to the k q1 and q3 over r13 square. So r13 is the distance between q1 and q3. So the F13 would be equal to k into 2 coulomb into 6 coulomb over 3 meter square. Now 3 meter square is actually 9 meter square when we square the its distance. So that would be equal to in the numerator 12 coulomb and in the denominator 9 meter square. So that would be equal to F13 vector is equal to, it's 3 and this is 4. So this is 4 over 3 k Newton, right? And now the net force on the charge, so the net force on the charge, net force on q1 charge is equal to, obviously the net force would be equal to F12 vector plus F13 vector. So now the F12 vector is, obviously it is 2k Newton, so this is 2k, and plus the second force, which is actually the F13, is equal to the 4 over 3k. So we can simplify it by using the addition of fractions. So this is this is would be equal to 3, and this would be equal to 6k plus this is 4k. Now we can write it by 10 over 3k. Now we know that the value of k is 1 by 4 pi epsilon naught, and the numerical value for the 1 by 4 pi epsilon naught is equal to, so this is 10 over 3k and this is 1 by 4 pi epsilon naught, and 1 by 4 pi epsilon naught has a value of 9 into 10 to the power 9, right? And since this is a force, we can write it write the SI unit for the force Newton. Now 3 and 9 is equal to 3, so this is cancel out each other, so 3 times, and so the force would be, the net force would be 10 into 3 is equal to 13 into 30 into 10 to the power 9 Newton. We can also write it that the F net is equal to 3 into 10 to the power 10 Newton, right? So this is the force applied on the q1 charge. Now let's deal with the direction So since we know that these two charges are positive, so these all charges are just repulsive. So repulsive means, like here we have a positive charge, let's say once again, here we have a positive charge q1 and there's a second charge q2, and both are positive, and the third charge is q3. So these are just positive. So q2 charge always applies force opposite to the direction of itself. So actually they repel each other, so they apply force in this direction. So this is F12, and the q3 charge applies force in a different direction, actually the opposite of r13. So this is the F13, right, direction of F13. Now the net force has the direction between, this is the angle between these two forces, right? So the net force would be direction of like this. So this is the net force, the direction of the net force. So F1 F net would have the direction this. So the charge goes like this in backside. So this is we can also know that this force is kind of repulsive force. So we have to write it here, repulsive, repulsive. Once again, repulsive, right? So this is repulsive force, and this would act on a charge q1 in a different direction. R1 vector is here and R2 vector is here. Fnet would act in a different direction completely with the F13 and F12, right? So probably you have get all these ideas about the principle of superpositions, and you must have the clear concept about how net force acts on a single charge and how superposition works. So let's meet in another video. Take care.